Right, I think it's time. Let me start the live stream for tonight. Okay, so hello, this is Junichiro Horikawa, and this is a Houdini algorithmic live tutorial live stream. And the topic for today is to implement a geometry processing for using Monte Carlo method, which is based on the idea by Rohan Sawhney and Keenan Crane from Carnegie Mellon University. The paper work called Monte Carlo Geometry Processing, a grid-free approach to PDE-Based method on volumetric domains. So this is to process a geometry, non-grid-based geometry, to deal just like a FEM. So FEM or PDE method usually needs a clean mesh like FEM to process the informations like, for example, like heat map and so, or like structural analysis and stuff like that. But seems like by using a method called Monte Carlo method, which is more of just a simple random walk method, which is pretty simple as in terms of the algorithm, which is currently being used in renderings mostly, but haven't been used in geometry processing till 2020. Seems like the Monte Carlo method could also be used for geometry processing, just like in renderings or image processing. And if you use that, it will drastically reduce the time of calculations. Seems it does have some issues like having a noise like this, which you can see on the middle, but the technique like denoisings for renderings could also be used for geometry processing, which have been mentioned in the paper. I haven't looked at how you could use a denoise like method, the denoise algorithm, which is being supplied by NVIDIA using deep learning techniques, but maybe I could search for how I could implement it for geometry processing later. But today I'm just going to try to implement how exactly I could use Monte Carlo method in order to do a simple geometry processing, just just like on the middle, or just like you could do something like this one. So by creating a boundary domains using a curve, or could be a surface, for a source geometry, and by just changing the domains, you could also change the inner like structures by using Monte Carlo method. Like you can kind of inspect which how each point inside this geometry could deform based on the outline deformations, which usually you have to calculate like PDE, or use a FEM method to calculate like heat map in order to define how each points be affected by the outline. But instead of doing that high cost estimations, seems like you could just use a randomness random walk in order to estimate how each point will move along with the boundary. So yeah, I thought that was pretty interesting and wanted to try out how that actually works. So that today I'm going to try to implement especially this type of deformations using Houdini. So it will be pretty simple in terms of the output, but the idea could be implemented in many ways, I thought. I mean, currently I'm working on a 2D surface which is going to be deformed by an outline curve, in this case a circle, but could also work for 3D mesh as well. And yeah, I mean, the outline, the boundary doesn't have to be the outline of the geometry. It could be within the geometry, just like you see on the paper. You have this middle line here. This could you could add several like boundary conditions in order to constrain the geometry, to control the geometry. So I thought, and I mean, it doesn't have to be deformations in terms of the processing it. You could also like calculate something like structural analysis, or just like you do in FEM and so on. Okay, so the possibility is pretty huge, I think. But as a first practice, I'm going to try to create some simple deformations using this method. Okay, so the example that I'm going to show you here is that by moving the control points of the circle, which is this one. So I started from the simple circle like this one, then deformed the circle just by moving the control points. In this case, I'm using a nerve type of the circle, then convert it into a mesh by using a resample. Okay. So in this case, I have only 5 control points for the circles, and by moving each control points, changing the outline of the circle, I could kind of deform the inner mesh info just by using Monte Carlo method. You see that each point within this circle mesh is being deformed along with the boundary curve, which is usually a bit hard to estimate if it's a mesh. If it's a nerve, there's a way, but if it's a mesh, it's pretty hard. So that's what I'm gonna try to implement today. So before going into the actual implementation, let's see what's the base algorithm for it. Okay, so I wonder if you know about the Monte Carlo method. I myself don't know much about it, but it's just a random method using a randomness in order to estimate the final results. For example, the most basic example you see for a Monte Carlo method is how you estimate a value pi. Monte Carlo method. If you look at the wiki, no, not this one. So I think this is a good example of how it explains how the Monte Carlo method could be used to estimate the value. So this is plotting the number of points within the square shape, and it's taking a ratio between the one within the arc and one which is not inside the arc. And if you calculate those ratios, it's the value is related to a pi. So and more points you have, more closest value it gets close to a pi, the actual pi value. So this shows that the number of samples, if you have enough number of samples for using randomness, you could kind of estimate the value, the final estimate, the precise value. So same for the geometry processing, you do need to have a tons of samples in order to estimate the precise positions. And even though you have enough samples, you do still get the noises, so in the end you might need to denoise. Okay, so that's the basic information about the Monte Carlo. Now, for a geometry processing, the main algorithm used is called walk on sphere. Okay, which is explained in the paper, which is this one. Yeah. So this is the most important algorithm for this processing, and if you know, once you could implement this, then that's pretty much it. All the rest is more of optimization stuff, I think. Okay. So let me explain how it works. So first of all, you create a domain. Any kind of shape, could be 2D, could be 3D, could even be 4D. And let's say you wanna know, you're going to have several points which you want to estimate how it behaves by changing the domains. Like for example, if you want to change the domains from the current state to something like this. So moving the boundary to this shape, and once you do that, you want to know how each point will be affected by this deformation. Okay. And in order to do that, you need to know how each point is being kind of attached to or affected by the boundary conditions, which is pretty much related to somewhere around here and also somewhere around here. Okay. So let's say this point, since this is close to a blue line, blue curve, could be related with this point with like, I don't know, 60%, with this point like 10% or 5% or so. So what you want to do is to know how each point is being related to each part of the boundary. Like this, since this point is close to somewhere around here, it could be related like 80% of the times the points being related to these boundaries, and 20% of the time it's being related to these boundaries, and so on. So what you want to know is to calculate the ratio, how much each point inside the geometry is related to the boundary or the domain that you want to control. Okay. And in order to estimate how much is being related to the boundary, you use a method called walk on a sphere. Okay. And I'll explain how that works. So let me go back to somewhere here. Let's pick one point on inside the geometries, and as an initial start, pick a point, random points inside the geometries, and the first thing you do is to look for the closest point on the boundary. In this case, the closest point could be somewhere around here, and calculate a distance between the closest point and the initial original point, and using that distance to create a circle or sphere. If it's 2D, it's a circle. If it's 3D, it's a sphere. Okay, then after that, you use a random value to pick any points on this circle. So could be somewhere around here, could be somewhere around here. Let's say you have just picked this point. Okay. Now from this point, you're going to do the same method, the same process that you have just done. Project this point to a project this point to a closest distance, closest point on a boundary. In this case, should be somewhere around here, and recalculate the distance again, and from there create another circle. And basically you do this until the circle becomes small enough, which is close to a boundary. So next step, get another points on the circle randomly, project it on the boundary, create a circle, and if you continue doing this, at some point the circle becomes very small enough to the boundary. And when the circle radius is being got small enough, like using some threshold, then you can stop at that time. And then you will what you need to do next is to see the property within that positions, the property of the boundary within that positions. So if it's curve, could be like a parameter value for the curve, like u value, curve u value. If it's a surface, could be a uv, something like that. uv or positions, anything, positions or deformations values, anything. It could be pre-calculated, or you could calculate it later. Let's say this is a uv value. Okay. And this is for a one sample, and you need to do the same process again and again with a different seed value for the randomness. So in the next step, from the same point, starting from the same point, the initial circle is the same, but there's a chance that you pick different points on the next step as a random walk. And from that point, you get a circle like this, and let's say you pick another point right here, and the next circle could be there like this, and the next point could be somewhere like this, like that, like that. So each time you run with a different seed with the randomness, you get a different goal. Okay, but the ratio, how much you get in terms of the goal, the goal you get by running multiple number of times, multiple number of samples using the same method, be related to kind of a distance from this point to the boundary. So if you, let's say if you try this like 1,000 times, you have more chance to get reach into these areas rather than these areas. Because the distance is short, so there's more chance that it's quickly go to these positions rather than going to these positions with more steps. So yeah, you have more chance to go in here, but less chance in going here. But having several samples or many samples to check, you can see how much you can check the ratio, how much each boundary point's being used for this exact starting point. Okay, which will result that you could kind of check how this point's being affected by each boundary. And well, since it's still using noise, I mean random values, you do get some noise, small noises, and you do need to denoise it in the last. But just by using this method, you could kind of estimate how each point is being affected by the boundary, and that's what I'm going to try out. So, okay, I have a question. Hey man, I was looking for your Houdini book, but I couldn't find it. Is there a place I can buy English version? There is a Gumroad website, which you can buy a book, self-published book. The one that I wrote for commercial, as a commercial book, was published only in Japanese. So yeah, if you could read it in Japanese, you might be able to get it. But let me just check where I can find it. So this is the one which I wrote in Japanese, which is, I believe is also available in Korean as well, but not in English, unfortunately. And there's also a book in Gumroad, which is just a simple self-published book. This is also available in English. I mean, not much text within here. It's more like a workbook. You have like 21 examples with English and Japanese, how you create each patterns, explaining how you create each patterns as an exercise. So if you're interested. So we're asking random points to the boundary, then using these scanned points to deform some geometry within. Yeah, that's right. Yeah, Elaine 2131. Yeah, you're right. You have to. You see Graphasia talk last. Thank you. Thank you very much. Yeah, I was pretty nervous at that time. Okay, so this is the basic algorithm. So first, let's try implement this so-called work on sphere on Houdini to see how we could actually create a sampling using this method. Yeah, so the idea is that after you have kind of get a ratio how much the initial points being related to the boundary, you could then you could then, let's say if you move the boundary like this, you kind of estimate by sampling how the points being related to each boundary, could kind of estimate how it should move based on the boundary informations, but based on the samples you got, like let's say 1,000 times or 10,000 times. Then using these 10,000 samples to estimate how points being moved, like for example, if the samples finished in this point, then currently the boundary is not moving, so there are no arrows on those areas. If the sample has been finished in this boundary points, then there's a chance that it's moving in this way, so you have this arrow being added to the point, and you just increment these arrows, these vectors movements based on where it has been finished on the boundaries. And after you have added all the like movements, deformations, you just divide by the number of samples you've used, meaning making an average. So think more like a like this, so number of forces divided by the number of samples will give you a average like force or average deformations informations in the end, and we'll give you an estimation how this point move in the end, how much it moves within the domain. Yeah, so that's the basic idea, and let's check it out how it works. So let's go. So first thing first, let's create a domain. Well, I'm gonna start by creating a circle, but it doesn't really have to be a simple shape. It could be really like complex geometries. But to check the algorithm, I think it's a good idea to start with a simple shape. So I'm gonna go with the simple circle first. Maybe if I have time, I'll try with a different shape. Okay, so let's have enough points on the boundary, since the resolution also matters. So currently I have, let's say I have 100 points on the boundary. Okay. Now, since I want to do some deformations, I want to create some patterns inside the circle. So let's create some patterns on the circle by creating some simple like boolean, I guess, with the font. I mean, anything is fine here. Let's say, what's the complex? I want to try with the complex letter as much as possible, which maybe I could try a Japanese font for that, or with the alphabetical font. Doesn't really have a complex like alpha at. Okay, we'll try with this one first. So I'm gonna trim this at mark with the circle as a test. So it had some interesting features like holes and some curves and like that. So I think it's a good thing to test. So I'm gonna extrude this just in order to be able to boolean with the circle. I'll translate this back a little bit. So I have extruded 0.2 on a distance, this z, negative z, positive z directions. So I'm going to subtract by 0.1, translate by 0.1 on z direction. Okay, then calculate the boolean, just trim out the circle with the solid that I have just made, the font that I just have made. Okay, it's not working, is it? So the boolean, okay, this has to be surface, this has to be solid. Okay. So I'm gonna try to deform this shape just by moving the control points of the circle. Now I realize I do need a control points for this circle, so instead of using polygon, I'm going to use nerves curve, and let's set divisions to something really low number, like 5 or 4, 5 maybe. Okay. And since this is a nerves, I don't think you could do a boolean, so you do need to convert it into a mesh later. So I'm gonna use a resample node, set the number of segments to 100, and then do a boolean. Okay, as an initial setup. Okay, then let's after this, in order to deform, you do need a bunch of points within this geometry, so I'm going to do a remesh. Now I realize this font have too much points, like you see here, so I'm going to reduce the number of points on this font beforehand. I'm going to use a remesh, resample. To reduce the number of points, and set the length to point, I don't know, 0.5 or something. Yeah, somewhere around here. Looks fine. Now, doing the remesh, going to set the target to 0.1 or 0.05. Also set the iterations for the smoothness to be high enough to have a clean mesh. Okay, so looks good. So I'm gonna try to deform this shape. So this is the basic setup for the geometry that I want to deform. Now the next step is to create a circle which I want to deform. Using the control points by just moving the control points. So currently I have 5 control points which I can move to deform, so let's create a edit node to be able to control these points. So I'm going to select one of them, use edit to be able to move like this, so which will deform a circle like this. So currently this is a nerves surface, so looks clean, but you cannot really use it for a mesh. So what I want to get is a kind of a similar result, similar shape result on a mesh. And for a mesh, I also want to get result like this. I mean, usually with this kind of simple shape, you could just use a UV map and so, but this is to test a Monte Carlo method, so yeah. And if the shape becomes more complex, then it will start to make more sense why we want to use this. Okay, but for now, we're gonna try with this simple examples. Okay, so I'll just go with this deformations just by moving 1 point. Okay, now I also need to make this polygon, so I'm gonna use the same resample node. Let's share the segment between this one and this one. Okay, so we have a same number of points with this one and this one. Okay, now for this resample, and the next step that I want to do is to make it as a curve, to be able to set it as a boundary shape. Since we want to calculate the distance, the shortest distance from each point on the mesh to this boundary. So for that reason, I think it makes sense to make this boundary a curve. If you want to use a surface as a boundary, then you could do another method. I think I want to try how I could implement this for a surface boundary as well, maybe if I have time. So now I have this boundary shape. Let's check the number of points if it's not changing. Yeah, the number of points is the same, so that's fine. Okay. Now that I have a boundary shape and the shape that I want to change, I also need an initial initial shapes curve. So I also want to have the curve informations for this shape as well, the initial shape. So let's do a same resample for this curve. I mean, I already did here actually. So I'm just going to create a polypath for this one as well. So I have three informations. One is the original circle, original boundary curve, the target boundary curve, and the mesh that I want to deform. It's pretty similar to how you set the bone in Houdini, like using deform bone structures. Okay, so after that, let's actually go into calculating a samples using Monte Carlo method. So the idea is to pick one of the points within the mesh that you want to deform. Like for example, pick one of the points, something like this one, and from that point create like several samples, maybe 1,000 to 10,000, in order to have less noises, to use a walk-on sphere method for this source geometry, source boundary, and then calculate how much that point will finish up on this boundary, and finish up in which part of the boundary for each point, and then use that information to relate with this deformed boundary to actually deform the mesh. Okay, so going to use a point wrangle, connect this mesh to a first input, and then connect the source curve, source boundaries to the second input, and then the target curve to the third input. Agent, any plan to translate your ebook to English this year? Well, unfortunately not this year. I am currently planning to write another book which is related to AVEX, which I hope is going to be published in English as well, but for the older works I don't have any plan to translate it into English. It's pretty much due to the publishers. I myself do want to have an English version, but yeah, I need to make publisher convinced that you do need the translations. Okay, where was I? So let's try with just one sample in order to see how it actually does, how it actually does calculate the Monte Carlo method. So I'm just going to work on the first points on the mesh, which is where, let me check, has to be somewhere within the mesh, so let's pick one of the points like 1174. Let's start from this point. So we're gonna just pick one point here on the point wrangle and try to do the process. Okay, so the process that I want to do is this walk on sphere. So the first step is to, from initial points, you look for the closest point on the boundary. So, which is pretty simple. You could use you just need to calculate the distance, the shortest distance to the boundary. So the easiest way to do is to use XYZ distance. Okay, that way, from the point you picked, you look for the closest point on the target curve, which is this one. So it should be somewhere around here where the closest point is, and then you could calculate the distance by using the XYZ distance. Okay, now you do want to get the informations where the point has been touched, so in order to get that information, you could get additional informations, something like the primitive number and UV with this XYZ distance function. Now in this case, I think I can just use this UV informations as an informations on the circle, which represents the position, the point positions on the circle. Okay, the exact point positions on the circle, which in our case is enough, I think. If you have multiple curves, then you also need primitive numbers as well. But in this case, there's only one primitive, so I think I can only choose single UV as an information to define where the point is. Okay, now after I have got the distance, which will be the radius for the circle, the next step is to pick random points within the circle. Could be here, could be here, could be here, could be here. Right, so let's do that. In order to do that, this is where I'm going to use a randomness. So I'm gonna name it as a direction and use random functions. And let's use point number as a seed. And what else? For now, I think just point number is fine, maybe together with some custom seed value, so that you can change some patterns, try out with different patterns. Okay. Now, this will give you a vector random value where the x, y, and z values in between 0 to 1. So I'm gonna normalize it. Before normalizing it, I am going to subtract with 0.5 for each coordinate, so that the range for x, y, and z become negative 0.5 to positive 0.5. Okay, now since the circle is within XY plane, you don't really need a Z coordinate for this directions, so you can kind of flatten the Z value to 0 in this case. If you're working with a sphere, then you do need all the information, so you don't really need this step. But if it's a flat circle, or if it's a flat curve, you do need to make it this flat for the randomness. Or the other method you could do to pick random points within the curve is creating a random UV by using something like this. Let's just use the same seed. And then, well, actually, I realize I don't really have a curve circle information, so maybe use this randomness as an angle, which in result you could use it together with cosine and sine trigonometries. And this will give you some random points on the circle. In this case, the radius of 1, so actually the radius is equal to d. Is it? Yeah. Yeah, it's d equal to d, so you have to multiply it by d. Okay, so this will give you another random directions. Okay, maybe this is better for a circle. I mean, if it's a sphere, I think this is much easier. This method is much easier. Okay, now that I have got the random directions with the distance, the radius, how much it will move from the center point. So what I have just created is this direction, the initial directions, how the initial point should be moved to go to the next point. Okay, and then from this point I should again project it on a surface, on a boundary. So, and I have to repeat this process again and again until the distance becomes small enough. Okay, so in that case, I think I do need to create a for loop. Could be a while loop, but I think it's using while loop is a bit dangerous, since there's a chance that it's not going to stop. So I'm gonna just use with the for loop. So to use the for loop, I think I'm gonna use it somewhere on here. Let's set the maximum number to check. Okay. Let's say, I don't know, 100 times, or maybe start with the 10 times. And let's open up the editor. Okay, so I'm gonna start by creating a count value, and each time the loop has got it to the end process, I'm gonna add the count by 1 and check the current count number. Okay, now after I have got the directions, I need to calculate the next positions. So, and the positions will going to change along with the for loop, so I have to create initial position value beforehand. I'm gonna name it as pos, starting from a current point position. Okay. Then instead of using at p here, I'm going to use a position. Okay. Now, I have said that you have to check if the distance is small enough. Okay, and if it's small enough, then you could just stop the process and use use the current UV that you have got as a final result. Okay, so create the conditions if d is smaller than some threshold value, then continue doing the process. Okay, and else, if the distance is small enough, then you can just break the loop. Okay. So within this conditions, what you want to do, first of all, you have calculated the directions. Then the next step is to update the positions with this direction, so that the new center points of the circle will become right here. And then on the next loop, you do the same process. You project that point to the boundary to calculate its small distance, get this distance value, and randomly pick the points using somewhere around here if the distance is small enough. I mean, big enough, bigger than the threshold. Okay, so let's see, what else do I need to do? And I also need to get the final UV value retrieved. So let's create a value called UV here, and instead of creating a new UV each time inside a loop, I'm just going to create a variable right here, and the UV will be updated each time this XYZ distance being called, so that we can just use the finalized UV in the end. This, I'm gonna call it TUV. Okay, and I think this is it for initial setup. Let's check the information. Now, I was working on point number 1174, so 1174 right there. You have got the UVs, but it's a bit hard to see if the process is correct or not. So let's just to debug, let's try to visualize this circles and see if the process has been done correctly or not. Okay, let's also check the count number. It says 0, so it doesn't look correct. Okay, that is because I don't have the threshold, I think. So let's set the threshold to something like 0.01. Set the max count to 100. Let's check it again. Okay, still 0, so maybe something is wrong here. So I guess I have to move this right here. Still not. Okay, so if the distance is small enough, count up the number. So I think I do have this loop here, accessing to the second input, which is the curve. Yeah. And then, I wonder why it's not being called. Oh, yes. Hi, Alan, thank you. Yeah, it has to be, the distance has to be bigger than the threshold. Yeah, you're right. Sorry. My mistake. Okay, now it seems to work. So we have to count. So just by creating two circles, you the point has been reached to the edge. Now if I change the seed value, it should change somehow, like you see here, because we're changing the samples. So sometimes you have bigger than 2, sometimes you have bigger than less than 2. Okay, so let's try to visualize this, how each point is being created. So in order to do that, I am going to create a point somewhere around here. First of all, create a new point at the new point where the current point position is. Then also set the radius, which is this one. Set point attriv. I'm gonna set it as p scale. Then also set the group so that I can trim that point just to check. So I'm gonna just name it as new PT. Okay, so the new point has been created for each loop with the p scale equal to d. So let's just try to pick that point up. I'm going to filter with the point, delete non-selected for the new point, so I can see 4 points or 4 or 5 points being created right there. And each point has a p scale value, so let's try to copy the circle. Open circle, open arc, the radius is equal to 1, so by copying it together with the p scale, the radius should be modified. And there you go. So the target, the source boundary looks like this, and the initial circle started from here, where the center point is the point that I have picked right here. Okay, should be somewhere around here. And then it seems like it picked this point as a random for the next random step, created a little bigger circle right here, and then the next step it picked right here, and the next step it picked right here, and ended up somewhere around here, making a small circle, small enough circle. And probably the UV value somewhere around here will be used for this sample. Okay, with another seed value, going to see different sample results. So you're going to have chances to go it into a different boundary positions, but with different ratios. Most of the time you get the points close to where the point is. You close the closest boundary points close to the original point positions, but at some point you also get the points on the other side as well. And more samples you have, more precise ratios you get. Okay, so let's look at the seed value. I think I also want to use this I value for seed as well, so let's do it like this. Okay. Right, so this is how the sampling works. This is how the walk-on sphere algorithm works. Well, this one seems to travel a lot, 16 times. Okay, so it's good, and that is for the 1 point, but what I want to do is for all the points. Okay, and actually I want to create more than like 100 or 1,000 samples per points. So actually you do need to loop. If you want to sample 1,000 times, then you do need to call this loop 1,000 times within the vex in this case. Now that might sound really high cost, and it is. So in order to prevent the loop as much as possible, and in order to use a vex functionality, the multi-threaded functionality as much as possible, one way to make calculations a little bit faster is to create initial samples beforehand. If you want to have 1,000 samples for each point, in this case each point on this mesh, then you could duplicate this mesh 1,000 times, then calculate the Monte Carlo for each point on the duplicate mesh. Then you don't really need to do the loop within the vex, which you could use the multi-threaded functions for the vex, though it'll be a little bit faster, I think. But the downside is that if the mesh already has a number of points like 10,000 or 20,000, then 100,000, then you're going to see tons of points being created initially. That might give you a bottleneck to the memory. So based on your memory, you might not want to do that. Based on memory, if you have a low memory, then you just want to do the loops within the vex. So I guess I'll show you both ways. First of all, without using a duplicate points from the remesh. So that's more straightforward. You just need another for loop and the number of samples. And let's start with 100. 100 sample is not enough in order to calculate in order to get the ratio along the boundaries. I think you at least need 1,000, and if you have 10,000 or 100,000, you'll be getting more precise informations, but then the calculation cost is much higher as well. So, but I think it's better to try out with the small numbers of samples. I'm gonna go with the 100 first. Then with this n value equal n being a loop for the number of samples, let's also create a randomness for this random c for with this n. Okay. And so each loop will get a different result like this, and I don't really want to create the new point anymore, so let's disable it. I'm gonna work on all the points. Okay, now so each loop within here, within the first loop, I am getting this UV value, which is going to be updated for each loop. So actually I have to bring this up to here, and in the end I want to gather all the UVs, all the counts, maybe not the count, but all the UVs to a single point as an array, I think. So let's try to bring that. And so currently I'm just promoting one UV attribute, but in the end what I want is the number of samples for each point. So need to create an array for UV, and let's also create the array for count as well. Okay, now So each time the loop has been exited, somewhere around here, I'm gonna append the updated UV to UVS array, as well as counts array. Then have to store that in the attribute so that I can use it later for deformation. I mean, I can do the deformation right here within this node, but I realized it, if I want to interactively change the deformations, then calculating the sample each time you deform might make less sense. So my plan here is to first of all calculate the ratios using the Monte Carlo method, then use that ratio later for the deformations. Okay, in this case the ratio is this list of UVs. Now the count list is just a metadata which I'm not going to use, just to check how much it used, how much circles it's been, how much passes, or how much cost it does take to travel from the initial positions to the goal. Now where it says 0, I think it's where you are stop because it's on the boundary already. So I realized if it's 0, it should stop. So the reason why it's not stopping is because I'm not having a break for this for the final loop. So let's check if the break has been done. I'm gonna call it a BR. If it has been braked, then you also wanna break it here as well. Okay, now, okay, well, maybe something is bad here. Maybe I should have done it right here. Let me check the conditions. So if started by BR equal to 0, okay, yeah, this should, wait a minute. No, it's not working. I think I should not do this. Okay, well, I think, well, yeah, actually I shouldn't do that. I mean, this is for each sample, so I shouldn't break the last loop. Sorry, I misunderstood. So I don't really need this. I don't really need these informations after all. Okay, so these are good. Yeah, each one represents the samples, the different values for each samples. In this case, we have 100 samples for each point. Okay, that's good. So we have 100 UVs as an information. Right. Okay, so now that we have enough samples, I mean 100 samples for each point, let's try to use that to actually deform the geometry. And I realize I don't really need to place this here, but I should need to use it in the next step. Okay, so let's create another point wrangle. In this case, going to connect the mesh first input, and then connect the source geometry to the second input, and then target the deformed target boundary to that third input. Okay, now for each point we have an array called UVS, so let's access to that information. I'm going to use for loop. To access the number of UVs, get the UV value, then this UV represents the point positions on a circle. Okay, kind of a primitive UV. So let's use that to access the actual point positions. Okay, so the source position can be retrieved by using prim_uv from the second input. I want access to point positions. The primitive number is 0 because there's only one primitive, and the UV is this. The target position can be retrieved similarly from the third input, P0 UV. So this is the corresponding point positions. Now let's calculate the deformation movement from source point positions to the target point position. So this is the directional vector value in order to transform this point position to this point position. Okay, now that I have got the directional value, let's create a final average directions outside the loop, and then append this direction that I've just created to the average direction. So increment this direction that has been retrieved by the UV informations, which represents the positions on the curve, positions on the boundary curve. Then after added all the directions retrieved from the boundary, the final step is to create an average direction just by dividing the number of samples. As a result, this average direction should represent the average deformation directional informations for each point. Now let's see by adding this average directions to the current point positions. And now you can see that the point has been deformed. You do see a lot of noises here, but at least you see a big gesture that it's being moving. Now let's try moving this original deformation control points and see how the deformations is working. Now I guess you don't really like this noise on the surface, but as a big gesture it does seem to work, right? Now let's try increasing the number of samples, where it was 100. So I've tried with 100. If I made it 10, it'll be much noisier. If I use 1000 points, going to see a lot smoother result. Now if you go with the 10,000 points, then it'll be more smoother, much smoother, but it will cost a lot of time, calculation time as well. You have to wait maybe around a minute to finish calculating, because you have to calculate like a double loop for each point. In maximum you have 10,000 multiplied by 100 loop, so it's a lot of loops. But as you can see, more samples you have, more cleaner results you get. And after you have calculated samples, The deformation part is pretty quicker than the calculating the walk-on sphere algorithm. So you could actually deform the geometry, not merely real time, but you could at least see the results in a few milliseconds. Just like that. Right? So this is the basic understanding, basic idea how this algorithm works. And by changing the informations, how you want to transfer the informations, like currently I'm transferring the informations for deformations, but doesn't have to be like deformations. It could be something like colors, it could be something like, I don't know, forces on the edge for structural analysis, just like you use in FEM. All sorts of stuff could be done here. Shall we try with the colors as well? So let's try to colorize the edge randomly. Let's say before modifying it, maybe somewhere around here. Do I need a polypath here? Yeah. So for this curve, let's say for 0 to 5, make it red. All the rest to white. Nope, it's been all the colors been set to red somehow. I don't know why. Points. Okay. Points. So let's say 0 to 10. I'm gonna set it as red. So let's see. Let's try to transfer this color to an inner mesh. So you have white colors on these boundaries, you have red colors on this boundary. And let's see how we can transfer these colors using a similar method. So I'm gonna copy this one, and instead of having the deformed curve as a target geometry, I am going to connect the colored curve on the third input. Let's call this color transfer. And this is where I'm calculating the deformation. So let's change this to get the color information, shall we? So the color, I just need to change this to CD, and the final color is final color from CD1 to CD2 is no, this is just a transferring value, so yeah. I'm gonna call this C direction and CD1. Now I might not, let's see. I might, well, let's try with this one. I mean, this might not be a good calculations for a color because it's a bit different with the vector value, but let's just see how it works. So pretty similar to how I used with the deform. I'm gonna calculate like this. Then instead of updating the color value, I'm going to update the CD value. See what happens. And actually I don't have initial color value, so let's make it white. And nothing seems to, okay, I see some gradations there. It's not really strong, not that strong. So on the edge has to be red, right? So it's based on the current color, so it's not really correct, I think. I shouldn't do something like this. Okay. Alright, so what I need to know, let's see. I think I just need the target curve. In this case, CD2. So let's just get the CD, the target color, then just add this to average color, and then average color you just need to divide it by the length of the samples. Then you're just going to use the average CD as a result. And like with this, you could kind of transfer the color in a smooth manner. Okay. So as you can see, this is similar to how you use with like structure analysis together with the FEM onto the if I set it to 30. Yeah, seem to work well. Let's try to mix some colors from 40 to 50. Let's use different colors like green, or maybe 30 to 50. Yeah, you see some mixes happening as well. So it could be used in many ways, I think. Okay, let me check the comment. It will be nice to use OpenCL for speed, but would need to implement XYZ distance and prim UV, which is problematic into and themselves. You're right, I thought about it as well. Using OpenCL makes more sense in this case because of the many loops we have here within this Monte Carlo walk-on sphere. Now, if you still want to do OMVEX, there's another way to make it a bit faster for this calculation. So let's try that method as well. So this is one method. Let's group this. Okay, so I'm gonna try another method which will vex friendly but need a lot of points. First thing first, let's go to a mesh, and I'm just going to get the points from this original mesh geometry because duplicating polygon is not necessary. I just need the points in order to calculate the samples, in order to calculate with the Monte Carlo method. I don't need a primitive, so let's just get the points by deleting everything but the points. Okay. And then this is the trick here. I'm going to use a duplicate to duplicate the number of points we have here. In this case we have 100,288 points. I'm going to decide how many samples we want to use right here inside the duplicate, which will create the vast number of points, which might be problematic if you have like trillions of points. So it really depends on how much you have initially. If it's like 1,000 to 10,000, I think that's fine. But if it's gotten more than like 10,000, 100,000, then using duplicate with the number of samples might give you too much number of points, will suck up your memory. So not a good idea, I guess. But at least with this way, you could use Vex to process each point simultaneously, so it will be much faster in terms of the Monte Carlo calculation. So let's try with that. Okay, so I am going to create another point wrangle. Let's copy the name here. Let's call this simul. And right here, I'm gonna connect this points, and also connects the source boundary to the second input. Then I'm gonna use a similar method, but instead of using the initial loop, I'm just going to use the last loop, because I already have enough samples. I already have determined the number of samples beforehand. I don't really need this loop here. So I can bypass this loop, which will, in the end, will be able to calculate in faster result. Okay, so, but at least I need to know which point that I'm accessing to, so let's get the informations, how many samples we have here. Okay, by copying this value right here. Okay, and let's try to create necessary informations like vector positions, vector UV. Already have a primitive. What else? In order to calculate the random seed, I don't need the num_n anymore, and I don't have a count. Okay, and the position is equal to the original point positions. That's the same. Now, what else do I need? So I have made the samples for each point. Actually, I realize I don't really need these sample numbers, I guess. Yeah. Because if everything is random, then that's fine. Then let's remove this parameter. Okay, so I do need to set the max count. Let's say 100. Threshold 0.01. Seed, some random numbers. Okay, and let's check the output. So in this case, I only get single value for each point, so let's get the UV, let's get the count, and check it out. Let's check with the geometry spreadsheet. So, single UV value and single count value. Now each point belongs to one of the duplicated points, okay? If you have 1,000 samples, then you do have 1,000 same points in terms of the positions. Now keep that in mind, and let's try to deform using similar things that I did here. So I'm gonna duplicate it here and try to use this information in order to deform. The result should be the same, but the calculation wise I have to do something different. especially somewhere around here. Currently you don't really have a array of UVs anymore, so instead you have to know how many samples you are using instead of these numbers. In this case, you're going to need to use this one. So I'm gonna copy this. This is where I need to set the parameter number of samples. Okay, and then use that right here. Now you cannot access from the arrays, but instead you have to access from the point attribute. So vector UV is point coming from a second input. You're going to look for the TUV attribute, and the point number is at ptnum multiply plus I multiply by n points. No, not the n points. Okay. I realize I shouldn't do like this because this point is already having tons of points, right? So I should not deform with these points, but what I should deform with is this the original geometry. So I should connect this mesh here, and I should use this just as a guide. So let's connect this to the fourth inputs. Made it a little bit complex than the original setup. Okay, so let's go back to where we were. So until here, that's fine. And we have vector UV, which is coming from the fourth input. And then we can then use this method. So if you have 1288 points for this mesh, the duplicated points will be added per 1288 points. Let's say if you say duplicate number of 2, then first 2, then from 0 to 1288, that's one set, and then the same set will be recreated again. Okay, so if you have 1000 set, you have 1000 sets of the same value, same points. Okay, keep that in mind, then you can access to each point, each corresponding points which shares the same positions by this index. Okay, then you can use this UV to get the source point positions, target point positions, and use a similar method here. Instead of dividing with the length of the UVs, use number of samples, and all the rest is the same, and we'll get the similar result. In this way, it's a bit faster. By changing the samples to 10,000, you can see that the result becomes a bit faster than this method, just having all the loops within one vex. Okay, but if you have tons of duplicates, you're going to see a tons of points right here, so that might going to be problematic. It's just the points, but yeah. If you have primitive, you're going to be definitely going to have a problem, so you should avoid having polygon when duplicating. And the deformation works the same. Right, Same for the colors. Let's try to set the colors as well. So bring it right here. So where did this come from? So I should connect the mesh here, the informations to the force input. All the rest I should make the similar modification that I did here. So I have a number of samples which I'm gonna copy this value here, then replace this one with here. The UV is just gonna copy this part. Gonna copy UV. Then the rest is pretty much the same. Gonna divide by the number of samples here, and there you go, same result. Okay, so that's one way to do, I guess, but in the end I guess it's better to use something like OpenCL. Yeah. Okay, so this is with the 2D geometries, and maybe I could also see how this works with 3D geometry. 3D geometry deformations. I mean, the deformation itself currently is more of a three-dimensional, but let's see if I can do a similar stuff with 3D. See how it works. So let's see. I'm going to create a platonic solid. This is nice, but a little bit too less points. Let's see. I'll try with the octahedron with this one. Could be interesting things to check. Or I don't know. Would it be better with the more curvy shape, maybe? Okay, so maybe I will use the icosahedron, and then use subdivide as a final geometry. Okay, this way, if I change the points, we'll deform something like this. We'll create some interesting shape. Okay, let's create two edits. One there, one here. Okay. Okay, and having a lot of depths to the subdivisions. Okay, this way I can have some kind of interesting deformations here for three-dimensional shape. And let's see how we could use the similar method that I have just done for 2D surface with these 3D surface. Shall we? Yeah, something like that. Okay, so what's to do? First thing to do is to create the original shape, which looks something like this, and I want to deform the inner structures of this shape with this deformed target. Okay, so I kind of need to create an inner shape. Maybe using volumes, maybe using some sorts of, I don't know, layers or something. Shall we just try with the simple, I don't know, gyroid shape from this spherical shape. So I'm going to create the, maybe I'm going to create the bound information, create a volume, density, then let's set the resolutions a bit high. I'm gonna use a volume wrangle to create the gyroid. X let's smoothen out the point positions to use it for an angle for a trigonometry, or scale it. So sine, cosine, sine, cosine p dot c, sine p dot c, cosine p dot x. Okay. Now changing the scale value to where I can see the patterns. Okay, somewhere around here. And since we want to deform the mesh, I'm going to convert it into a mesh, so using something like convert. Okay, let's try to make it a bit more high detailed like this. Okay, let's also increase the sampling divs. Okay, made it a bit smoother. Now let's trim this shape with the original boundary shape. Boolean. And no, the other way around. Comes here, comes here. We want to get the intersect. Okay, so what I would like to do is to transform or deform this shape using this shape, and the goal is to see the deformations inside the structure. Okay, how the inside will be deformed together with the outside surface. So that's our goal. Okay, so do we have enough informations? I guess we have an outer surface, we have a inner surface here, we have a target geometry, the source geometries, and okay, so pretty much we have enough informations. Let's try to do the similar stuff here. So we have, let's use which method should I use? Since this is faster, I would like to use this method. I'm gonna comment it as faster but memory killing. But I just say slower. Okay, so I'm going to just get all this batch, copy it. Okay, and try to modify what I have here for this surface-based deformation. So first thing first, we can connect the one that I want to deform, which is this one, to here. Make a point, make a bunch of points and duplicate it. And I'll try with the small number of point samples for now. Okay, and also, since these points are going to be moved, I think it's a good idea to make it triangulated mesh instead of having more than 3 points for each mesh, for each polygon. So let's triangulate it beforehand. I'm gonna use a remesh and something like this. Yeah, looks okay. Okay, fine. Okay, then we got the points, and we have duplicated the points here. That's the initial step. Now, next we have a Monte Carlo, and we have to input the source surface into the second input. So the source target, source geometry is this one. Now, in order to kind of know, at least what we need to know is how each point is corresponding this geometry and this geometry, right? Now, one way to correspond the two different geometry which shares the same point numbers is to use UV or point number, but in this case I think using UV is fine, right? And actually using primitive UV is just fine instead of creating your own UV, which might gives you some errors. So instead of using custom UV, I'm going to use a primitive UV. Okay, so look, let's connect this mesh right here and target mesh. No, I don't really need a target mesh yet. Okay, so let's get inside. Let's see where I should change. Okay, so right here, this was only for a circle shape, right? And it's not for a three-dimensional sphere when we travel around the boundaries. So we have to change this random directions which suit with the three-dimensional sphere. So the random seed is fine. I'm just gonna copy it, but instead I'm just going to create the random vector first, then subtract it by 0.5 for each coordinate, normalize it, then multiply it with direction, distance, the radius. Okay, I think that should do it. All the other part, I think I can just go with these. Okay, hopefully. Now let's go to the deformation. Now I don't use the polypath anymore. So for this one, what I want to deform is this remesh geometry. For the second input, I need to input this subdivide node, and then I need to connect this one right here. Now I realize I need to also bring up additional informations, not just UV but also a primitive number, because we have a lot of primitives. You can see you have tons of faces here, so you do need to actually know the primitive numbers. So let's bring that up as an attribute. Okay, then I think we are ready to go for deformations. So we have number of samples, which should be coming from here. Let's copy this. Then TUV is fine. Now right here we have to use a primitive number coming from the fourth input. So let's get that. Int prim is equal to 3 t prim, same point number. Okay, then put it here. Okay. As a result, I'm seeing some deformations happening. And if we check the target geometry, yeah, it is within the target geometry. And if I try to deform the shape, you see inner shape is being also deformed along with the boundary. Now the sample is currently 100, so it's a bit low. Let's increase the samples to something like 1000, which will give you a smoother result. Still, the deformation speed is pretty nice. Yeah, interesting enough. And let me why can't I edit this one? Oh. Okay. So, where was I? Yeah, so it's working. So even with the 1000 samples, the mesh seems clean enough. If you increase the samples to 10,000, might become better. The initial calculation takes a little bit of time. Most of the calculation is taking time is somewhere around here. Okay, it's taking a little bit of time. Why is that? Do I have too many points? Maybe. Okay, now it's done. So how many points we have? Okay, it's a lot. Well, so 60 million points, that's a lot. So maybe gotta be careful with how much points you're dealing with. Okay, and if I try the deformations, yes, the deformation itself works in decent speed, I guess. And you'll see interesting deformations happening just by changing the boundary. So, seems to work with the mesh as well, right? Okay, I'll make this back to 1000. So this idea, using Monte Carlo method for geometry processing, could be really interesting. And you don't really need high spec machines to calculate PDEs, which usually takes like an hour or more. So yeah, it's good, very good. And it could also work with dirty meshes, not really clean meshes, so that's one of the benefit you have as well. Now one thing I want to try, not today, but to use a denoise algorithm based on deep learning stuff to clean the final result. As you can see right here, you do see some jiggles still. To make these parts smoother, you might need a denoise post-process, just like written in the paper. Okay. So that's one thing I might want to do. I want to try at some part and sub point. Now, you could kind of fake this smoothness by adding something like attribute blur and smooth out the directional vector value, which might give you, is this a directional value? No, actually not. Okay, so you could kind of fake this deformation by adding a attribute blur to this average directions that I have created. So instead of directly applying the average directions to the point, let's create the directional attribute, apply average directions, smoothen out using attribute blur, smoothen out the directions, then apply that attribute to the point. Okay, so with that you see a little bit smoother result, but it is kind of a fake, so, and you are having some issues on the boundary. You still have some boundaries because you're pinning the border. If you unpin it, all the rest of the borders also be smoothen out. Might be a problem. But yeah, if you need a smoother result, that's one way to deal. If you don't have it, the result looks like this. Okay, so probably for this part, using denoise like algorithm, something from NVIDIA might give you a better result. Okay, I'll just apply this right here. Okay, so far I've explained what I wanted to explain for today. Let me know if you have any questions, or if you want to see how this could be tried out in different ways. Let me just try with these colors as well. So this was the color for the target, so let's change the color for right here. No, change the color for this part here. How does this give you the color? Interesting. I guess I shouldn't set the color like this. Maybe I could sort the point based on the, I don't know, y value. That way I could create some gradational stuff. So from 0 to 30 red, 30 to 80 green, or maybe a lot more, 200. Okay, 100 to 200, 0 to 100. And let's also blur this a little bit. Okay, so let's see how this color will be transferred to a inner geometry. Okay, so the original geometry is this one, right? The second input will be the non-colored geometry, which is, I don't know, maybe the same geometries. Oh, wait a minute. The first input, okay, I don't actually need a second input after all for the color, so nothing is necessary. Okay, do I? No, I don't think so. Then I have num samples, average CD, UV is getting from the fourth input, and now I think I need to change these part. Do I? Yeah, I have the UV, and I need to create the primitive as well. T-prim, and using prim here. Alright, so the color is being transferred within the jaw structures as well, like this, and looks interesting. Yep, so this is how it works. Monte Carlo sampling for deformations and coloring. The algorithm itself is pretty simple, but it's pretty versatile in terms of the tool. You could, there's many, I could think of many possibilities could be used in many ways, so I hope you do the same. Okay, I guess this is it. If no questions, then I will finish the live stream. Hey. Maybe this might be too boring, but I hope you see some interestingness in this algorithm, just as I saw it. Let me just clean this up and I'll finish this live, since I have too many networks here and there. Okay, so for this one, Source 3D. Okay. Gonna use an object merge to transport this geometry. Okay, so should be connected here, here, and this is the geometry to modify. I'm just gonna call it Geo 3D. As always, I'm going to upload the file to a GitHub as well as Patreon page, so that you can download the files from those pages. I'll paste a link to a description page of this YouTube live stream, so if you come back later, you'll be able to, should be able to download the file. Okay, so if you're interested. Okay, then comes here. This comes here. You have the target. Alright. If you have any idea how this could be used in some different ways, let me know. I'm looking for some ideas. So, I'll end. I wonder if this can be used to calculate skinning informations for bones deformations. Each bone finds each surface points it could affect. Then a process applies the weighted percentage of all bones. I think it could be used. I think each bone finds each surface points it could be affect. Then the process applies the weighted. Yeah, I think there's a possibility to be able to estimate instead of, like, most of the time in Houdini when you estimate the weight you use something like tet embed or tet conform, I think, which is to create a tetrahedron shapes within the mesh in order to estimate the weight. But you could do the similar stuff with these method instead of using this one, for sure, I think. So I think there's a possibility. Although this is simpler because you already have a node. You do need to kind of set up yourself because there's no available node. Maybe if you make it as a node, might make more make sense. And still some issues with the noises. You do need to have tons of samples in order to make it clean weight. So probably you might need to blur it in the later part. You do need to denoise it as a process or faking by creating a blur or something. But I do believe it's possible. Okay, where was I? So that's for the 3D. Let's also organize the 2D part. Okay, so target 2D. And then and right there. This is the source 2D. Okay. And just with the point cloud, yeah, point cloud would also work because you're just calculating. I mean, you don't really need a polygonal informations. You just need the point in order to calculate like the Monte Carlo method. So point cloud definitely works. Okay. Okay, coming here. Okay. And finally, this mesh. Geo2D. Oops. Okay. And I think we're ready. Okay, so this is for 2D. This is for 3D. All right. So I guess this is it. I was wondering if I could come up with some process which is other than what I have just tried out. Looking back at the paper, the example it shows are something like cross-field correspondence, quad layouts, which looks interesting. Culture. I don't know what is being done here. I don't really know. It says input is like this, and you seem to be able to calculate the flow or Helmholtz decompositions on a 3D domain. Monte Carlo approach, entirely avoid meshing of the domain, setting up matrices, solving it. No idea what's doing here. Now this was straightforward, yeah. So you could see how this could be work by our examples. And there are a lot of optional informations how this could be more stabilized. But the main part, I guess, is what I've just done. Yeah. Okay. So maybe I'll do another live stream if I come up with some interesting way to use this. But for now, deformation is straightforward implementation for this Monte Carlo method. So, yes, I'm satisfied. Okay, that's it. Thank you very much for watching, coming here, giving me a comment. A lot of great feedbacks. Thank you. Okay. And good night. I'll upload the file later. Just finish with these. Okay, I'll end the stream. By the way, this could also come here to combine these two colors and deformations, just because I'm not changing the primitive number and the UV is the same. Oh well. Thank you. Good night. See you next week.